Black hole information paradox. You drop a hard drive into a bonfire, and you watch the data burn. The patterns are gone, but in principle, the atoms and heat still hold traces. Now, swap the bonfire for a black hole, and the rules get ugly. Physicists led by Stephen Hawking found that black holes leak a faint glow now called Hawking radiation. Over time, a black hole could shrink and vanish. If that happens, what happens to the information that fell in? Quantum physics says information cannot simply disappear. That rule keeps cause and effect tidy and underpins how atoms behave. General relativity paints a different picture. It treats a black hole as a one-way trap where anything that crosses the horizon is lost from our universe. Two great pillars of physics seem to point in opposite directions. One says information survives. The other says it is gone. Here is the strange part. If information really vanishes, then the mathematical rules of quantum mechanics break. That would mean physics is not just unfinished, it would be inconsistent. Physicists call that a crisis. Over the decades, a few bold ideas tried to fix it. One proposal from string theory says black holes are not empty inside. They are fuzzballs made of countless tiny strings that store information across their surface. Another idea says the horizon wears what they call soft hair. Tiny low-energy fields sit there and act like a memory. There is also a no-hiding idea from quantum information. It says that if information appears to vanish from one place, it must move somewhere else. Experiments on small quantum systems have shown lost information can hide in the environment. But none of these fixes gives a simple, widely accepted picture yet. So here is the cliffhanger. If information escapes, how exactly does it come out in Hawking radiation without breaking quantum rules? Physicists proposed three big fixes. One idea from string theory says the interior is not empty. Instead, it is a tangled web of tiny strings and brains. Those microstates store the details of everything that fell in. Call it a fuzzball picture. If that is true, then information never disappears. It is woven into the black hole from the start. A second idea says the edge of the black hole is smarter than we thought. Low-energy fields living on the horizon act like memory. Physicists call that soft hair. Those tiny wiggles could record who went in and whisper it back out as radiation. That would let information hitch a ride out without breaking quantum rules. A third approach comes from quantum information science. The no-hiding insight says lost information moves into the environment. Tests in tiny quantum systems recovered data that seemed to vanish. This hints that Hawking radiation might carry hidden correlations that reveal the original information if we know how to read them. There are more exotic proposals. Some suggest that space-time itself stores a memory at the smallest scales. Others point to holography, where everything inside is encoded on the boundary. Each idea has strengths and big open questions. We have hints from gravitational waves. We could also search for subtle patterns in radiation that betray encoded information. But making that measurement is fantastically hard. Here is the blunt truth. If none of these fixes work, then the sacred rule that information survives must be revised. That would mean rewriting parts of quantum theory or general relativity. Which of these paths actually leads to a consistent universe? Schrödinger's cat. You close a sealed box with a cat inside and a strange device. The device has a tiny chance to release poison, depending on a single radioactive atom. Quantum rules say the atom can be both decayed and not decayed at once. That makes the whole setup both alive and dead at the same time. Here is the trouble. In everyday life, things are either one thing or another. You do not expect a cat to be both alive and dead. Quantum theory, at least in its simplest textbook form, says the wave describes both options until someone checks. The act of checking turns one possibility into reality. That is the measurement problem. Who or what decides when a possibility becomes a fact? Physicists offered different ways out. One choice is to accept a collapse rule. The wave jumps to one outcome when measured. That saves our common sense, but adds a rule that feels like a patch. Another choice is many worlds. Every possible result happens in its own branching universe. In that view, the cat is alive in one branch and dead in another. You live in one version and never notice the split. Both options have weird costs. Collapse introduces a special rule that singles out observers. Many worlds multiplies reality into an infinite tree. Each answer fixes the paradox in a way, but creates a new headache for how to think about probability and experience. So, which is true? Do measurements force reality to pick one path? Or do we live inside a grand branching multiverse? Scientists moved from thought to test. One new method uses clever games to check superposition directly. Researchers adapted an XOR game and measured copies of the same photon state. With just 37 photon copies, they reached over 99% confidence that superposition was real. That is not philosophy. That is lab work. Other experiments look at the measurement devices themselves. A two-photon interference trick, called Hong-U-Mandel, shows that detectors can share quantum correlations. Vishwas KS proposed a setup where the measuring device itself can be in superposition, and the interference pattern reveals that fact. Those ideas make the collapse question experimental. Then there is the quantum Zeno effect. At Lund University, researchers watched a tiny system of two quantum dots, where frequent observation slowed the system down. By strengthening the measurements, they effectively froze the evolution. That shows that measurement strength matters in a very real way. Interpretations react differently. Art Hobson argues the measurement state is a non-paradoxical correlation. Many worlds says every result happens in some branch. Other scientists still consider whether consciousness plays any role. The experiments do not yet force a single picture. They do trim the wildest guesses. So here is the moment that turns the thought experiment into a scientific puzzle. We can set up tests that pick between collapse-like rules or branching worlds or environmental hiding. The data is beginning to speak. Which story will the evidence back, and what will that choice do to our idea of reality? Zeno's paradoxes. You are watching a race. Achilles is sprinting. The tortoise has a small head start. Achilles runs faster. He will catch the tortoise, right? Zeno said not so fast. He argued that Achilles must first reach the spot where the tortoise was. While he does that, the tortoise moves on. Then, Achilles must reach the new spot. That keeps going forever. A race that never ends. The point is not sport. It is infinite division. Zeno used the idea to show motion looks impossible if you slice time and space into forever smaller pieces. He had another version called the arrow. At any instant, the flying arrow is where it is and not moving. Put enough instants together, and motion disappears. For centuries, people accepted the puzzle as a curiosity. The real fix came with math. Calculus and the idea of converging sums showed that an infinite number of smaller steps can add to a finite distance. The trick is the infinite series that shrinks quickly enough. Achilles does catch the tortoise. The arrow does move. That mathematical answer felt like the end. But physics asks a harder question. Math treats space and time as continuous. Do they really behave that way in nature? Modern ideas suggest space might be grainy at unimaginably small scales. If space is discrete, then the way motion works could change. Zeno forced us to invent calculus. But if the fabric of reality is not continuous, what new rules will we need next? You might think Zeno was solved and the book closed. Mathematics gave us calculus, and the race ends. But modern physics asks a different question. Does nature actually behave like the continuous line that calculus assumes? Some leading ideas say no. In approaches to quantum gravity, space and time may not be smooth. Theories like loop quantum gravity picture space as made of tiny building blocks. Other proposals use discrete chunks at the smallest scales. If space is grainy, then motion might not be a smooth slide. It could be a series of jumps. That sounds abstract, but imagine walking across a tiled floor. If the tiles are huge, and you hop tile to tile, you do not trace a continuous curve. Zeno's worry returns in a new form. If motion is a sequence of tiny hops, then the rules that rely on smooth continuity might need to be rewritten. Can we test this idea? Not yet directly. The scales involved are far smaller than atoms and far beyond present experiments. Physicists search indirectly by looking for tiny violations in symmetries or in high-energy events. Gravitational wave data and particle experiments put limits on how weird space can be. So far, those limits keep most discrete models under pressure, but not ruled out. The deeper point is this: Zeno forced a revolution in math. Modern paradoxes may force a revolution in the way we model space and time. If continuity fails at the smallest scales, what happens to motion, cause and effect, and the laws built on those ideas? Grandfather paradox. You climb into a machine and step back into your grandfather's youth. You do something small, and suddenly your grandparents never meet. If they never meet, you are never born. If you are never born, you could not have traveled back to stop them. The scenario eats its own cause and effect. The problem is simple and brutal. Time order matters because causes produce effects. The paradox shows that if you can change the past, you can create logical contradictions where events erase their own reasons. Physicists take that seriously because logic is what makes predictions possible. There are three broad responses. One says the past is fixed. You can revisit it, but you cannot change it. Any attempt to alter events will fail in some unexpected way. Another says time splits. If you change something, you create a new branch where outcomes differ, but your original past still exists. That avoids contradiction by multiplying histories. A third view says macroscopic time travel is impossible. The universe has safeguards that prevent causal chaos. Some thinkers formalize these ideas. The self-consistency idea says only actions that do not create contradictions can occur. Stephen Hawking offered a chronology protection notion that nature prevents closed time loops. Others point to quantum branching, where every choice spawns a separate history. Which answer feels right depends on which rule you trust more. Do you prefer a single, consistent past that never bends? Or do you accept a multiverse where your interference lives on in a different branch? Or does the universe quietly stop you from breaking causality? Physicists formalize the paradox into rules. One rule is self-consistency. It says any events that happen must fit together without contradiction. If you travel back and try to change something, your actions find a way to fail, so consistency holds. It is like a puzzle that refuses a wrong piece. Stephen Hawking argued for chronology protection. He suggested the laws of physics prevent closed loops in time from forming. In Einstein's equations, you can find solutions that look like time machines. Wormholes and certain rotating universes allow closed loops on paper. But those solutions usually need exotic conditions, or they fall apart when you add realistic effects. Quantum mechanics adds its own twists. Some proposals say quantum uncertainty and decoherence smear out paradoxes so that contradictions never become definite. Other ideas use branching worlds. In that view, changing the past creates a fresh branch, where the change lives, but your original history remains untouched. There are also technical results. When researchers add quantum fields near a would-be time loop, the energy blows up and the loop destabilizes. That gives a mechanism for chronology protection. On the other hand, some controlled toy models show consistent solutions that let information loop without paradox. The debate is alive. What matters is the consequence. If nature enforces consistency, then time travel is a polite illusion. If nature lets branching histories exist, then causality becomes plural. If neither holds, we may be forced to change the basic logic physicists use every day. Maxwell's demon. You have two gas chambers, separated by a tiny door. A clever little being opens the door when a fast molecule approaches and closes it for slow ones. Over time, one side heats up and the other cools down. You can run an engine with that temperature difference. That seems to beat the second law of thermodynamics. The second law says disorder, or entropy, tends to increase in a closed system. Maxwell's setup seemed to make entropy fall for free. That is why it grabbed attention. Physicists asked how the demon could sort molecules without paying a price. The answer came from thinking about information. Leo Szilard showed that even a single molecule engine needs a measurement. To extract work, you must know where the molecule is. Recording that fact uses memory. Later, Rolf Landauer clarified the cost. Erasing stored information releases heat. That heat exactly balances the apparent gain the demon made. The second law survives. In plain terms, the demon can collect data and cheat for a while. But when it clears its memory to keep going, it must dump heat back into the system. Information processing has a physical price. That insight founded a whole field that links computation and thermodynamics. Experiments have since built tiny engines and demonstrated the trade-off between information and energy. So Maxwell's mischievous creature lost his free lunch. But a final wrinkle remains. At quantum scales, information behaves oddly. Could exotic information protocols let us squeeze more work than expected, or reveal a deeper limit we do not yet see? Maxwell's demon. Laboratory work turned a thought experiment into measurable physics. Teams built microscopic engines that trap single particles. They measured the tiny heat released when information was erased. The results matched Landauer's prediction. Erasing memory produces heat. Information processing has a cost in energy. Researchers then made quantum versions. They set up quantum Szilard engines and experiments using single photons and superconducting circuits. In those systems, entanglement and coherence change how information is stored. A quantum demon can use correlations that classical demons cannot. That opens new possibilities and new limits. None of the experiments gave a free lunch. The apparent gain is always paid back when one accounts for measurement, memory, or decoherence. Still, the quantum case is subtle. Entanglement can hide information in non-local correlations. Reading that information may require joint operations that have their own energy price. The bookkeeping becomes tricky. Why should you care? Because these principles set the ultimate efficiency limits for tiny machines and for quantum computers. When engineers design processors at the smallest scales, they face the same trade, Maxwell pointed out. Information is physical. Energy and computation are two sides of the same coin. So the demon did not break thermodynamics. Instead, it built a bridge between heat and information. Yet a real question remains. Could future quantum protocols or exotic correlations let us tilt the balance in ways we do not yet understand? If so, some of our core assumptions about energy, information, and work might need to be rewritten. Twin paradox. You and your twin make a promise. One of you rockets into space at near light speed and then comes home. The traveling twin returns younger. That sounds impossible. You both see the other S clock run slow. So who really ages less? Special relativity gives the answer. Observers moving relative to one another measure time differently. Each sees the other S clock tick slower. The key is not symmetry. The traveling twin changes motion. They speed up and slow down to turn around. That break in symmetry picks out one frame as special. The traveling twin experiences acceleration and a different sequence of events. That is why their total elapsed time is less. General relativity joins the story. Gravity and acceleration both affect clocks. Clocks deeper in a gravity well tick slower. That means motion and gravity combine to set who ages more. This is not just thought. Experiments prove it. Physicists flew atomic clocks on jets and compared them to clocks left on the ground. The flying clocks showed the predicted time differences. High-energy particles called muons live far longer when they race through the atmosphere than they do at rest. That is time dilation in action. Even the network that guides your phone and navigation uses these corrections. GPS satellites must adjust their clocks for both motion and gravity, or your position would drift. So the paradox changes from a logic puzzle to a reliable physical effect. The real question now is where the simple rules of relativity meet extreme conditions. You already know the basic outcome. Now consider how solid that result is. In 1971, physicists flew atomic clocks on jets around the world and compared them with clocks on the ground. The differences matched relativity's predictions. High-energy particles in accelerators also live longer when they race. These are not thought experiments. They are measured facts. Precision keeps improving. Optical atomic clocks now detect time differences over distances of just a few centimeters. That means gravity's tug on time is measurable in a single room. Engineers use that knowledge to calibrate instruments and to push navigation and sensing to new limits. The twin paradox works in practice. The surprise arrives when conditions get extreme. Near light speed, travel, or regions near a black hole. Combine strong gravity, acceleration, and quantum effects. We do not yet have a full theory that marries quantum mechanics and general relativity. That gap is where paradoxes lurk. If time itself becomes fuzzy at the smallest scales, or if quantum gravity changes how clocks tick, then simple predictions about who ages less could shift. Practical impacts follow. Space travel at relativistic speeds would face new navigation rules. Atomic clocks used in experiments might show anomalies. The neat symmetry of relativity could bend in unexpected ways. So the twin paradox is both solved and unfinished. It proves that our equations work across many tests. But it also points to the boundary where our best theories stop holding hands. How do you reconcile time dilation with a universe that allows time loops and causal puzzles? That harder question leads directly to paradoxes that let events appear out of nowhere. Bootstrap paradox. You receive a manuscript from your future self. You publish it, and decades later, you travel back and hand that same manuscript to your younger self. Who wrote the book? The manuscript exists, but its origin is missing. That is the bootstrap. It is a closed causal loop where an object or piece of information appears without an initial creation. There is no inventor, no first cause. The loop feeds itself. It feels like theft of existence. It is not a contradiction in events. The loop is consistent. Yet it breaks the usual story of how things come to be. Physicists notice two problems. One is logic. If something has no origin, it challenges explanations based on cause and effect. The other is information bookkeeping. Where did the pattern of the manuscript first come from? That question matters because physics cares about where properties and information originate. Some solutions keep the loop tidy. The Novikov self-consistency idea says if a loop exists, then events inside it must fit together. You cannot create a contradiction. The manuscript you hand your younger self must be the very same manuscript your younger self later publishes. There is no origin, but no logical error either. General relativity shows how closed time-like curves can appear on paper. Wormholes and exotic rotating universes allow paths that return to their own past. Those solutions make the bootstrap scenario possible in theory. The trouble begins when you add quantum fields. Then, energy around the loop can spike and destabilize the solution. That mechanism gives a practical barrier to stable time loops. Physicists study toy models where quantum effects are simpler to control. Some of those models find consistent loops that do not blow up. Others show instabilities that destroy the loop. The outcome depends on fine details. The hard fact is, experiments cannot probe these regimes directly. The scales and energies involved are beyond present technology. The deeper worry is informational. A bootstrap object carries structure and patterns that did not originate in the usual sense. That strains conservation ideas and our sense of creation. If the universe allows self-formed loops, then information can appear without an initial origin. That undercuts how scientists trace causes and histories. So we have three live possibilities. Loops are allowed and self-consistent. Loops are forbidden by quantum back reaction or some chronology protection. Or loops force branching histories where origin shifts to a different history. The deeper sting is philosophical. If ideas or objects can bootstrap into being, what happens to responsibility, to creation, and to conservation of information? If a design can appear with no inventor, then the notion of cause is weakened. EPR paradox. You have two particles created together and sent far apart. Measure one, and you instantly know the other S property. Measure a different property, and the outcome on the distant particle changes too. That felt like spooky action at a distance to Einstein. Einstein, Podolsky, and Rosen used this to argue quantum theory must be incomplete. They wanted hidden variables that secretly set outcomes before measurement. If such variables existed, physics would be local and tidy. Quantum mechanics offered a different story, where outcomes are not fixed until measured and entangled particles share correlations that defy local explanation. John Bell turned the argument into a test. He showed that any local hidden variable idea must obey an inequality. Quantum mechanics can violate that inequality. Experiments could then decide between local hidden variables and quantum non-locality. Experimental tests began in earnest decades later. Alain Aspect S experiments in the early 1980s closed many loopholes. Teams since then tightened the tests and violated Bell-S inequality repeatedly with stronger controls. Entanglement is real and robust. Distant particles show correlations that no local hidden variable model can reproduce. That forces a tough choice. Either the world allows non-local correlations that look instantaneous, but do not carry usable signals, or our assumptions about reality and separability are wrong. Entanglement does not let you send messages faster than light. Yet it suggests a deep connection that crosses space, which is more unsettling. A universe that secretly links distant objects, or a universe where measurement itself scrambles the idea of independent reality. Aspect, and many teams after him, tightened the tests. They separated detectors far enough to force decisions that could not casually influence each other. They improved detectors so missed events no longer skewed results. Those upgrades closed major loopholes and strengthened the case that nature violates Bell-S inequality. Still, entanglement does not let you send a message faster than light. That is the subtle part. The correlations look instantaneous, but they cannot be controlled to carry information. Physicists call that the no-signaling rule. You can predict statistics, not specific messages. That odd mix keeps relativity intact while honoring quantum weirdness. Practical work grew from these paradoxes. Labs built quantum key distribution systems where entangled particles create provably secure keys. Teams teleport quantum states between labs using entanglement and clever classical channels. Quantum computers exploit entanglement to solve problems in ways classical machines cannot. The paradox moved from philosophy to engineering, yet a conceptual gap remains. If particles share correlations that defy local explanation, then what is the underlying story about information and space? Some researchers explore whether entanglement is a clue that space itself emerges from information. Others ask how entanglement behaves near gravity wells or inside black holes. That is where the EPR puzzle reconnects with the black hole information problem we met earlier. So here is the tough question. If entanglement can link distant systems, and if black holes hide and scramble information, could these two puzzles be the same knot in different clothing? Olber's paradox. You step outside on a clear night and look up. The stars are scattered like pinpricks. The sky is mostly black. That seems obvious until you run the logic backward. If the universe were infinite and unchanging and filled with stars everywhere, then every line of sight should end on a star. The night sky would be as bright as the surface of a star. Darkness becomes impossible. That simple reasoning made the darkness at night into a real puzzle. People tried fixes. Some blamed dust between the stars that hides light. That fails because the dust would heat up and glow itself. Others suggested limits on stars, but those ideas felt ad hoc. The paradox forced astronomers to ask deeper questions about the whole cosmos. Two facts resolve it. First, the universe has a finite age. Light from very distant stars has not had time to reach us. The sky is dark because the universe is young enough that not every direction contains a visible light source yet. Second, space is expanding. Light from distant sources stretches to longer wavelengths as space grows. What was once bright, visible light becomes faint infrared, and then microwave. The cosmic microwave background is the ghost of a time when the universe was hot and bright. Now that light is cooled and invisible to our eyes. Those two ideas do more than explain the night. They changed cosmology. They point to a dynamic universe that had a hot beginning. They turned a poetic question about darkness into evidence for a cosmic story. But here is a twist that keeps the mystery alive. If the universe keeps expanding and stars burn out, what will the night sky look like in the far future? Will it become darker still, or will some surprising process light it up again? Think ahead to the very far future. Stars burn fuel and live for a long time. Red dwarfs glow far longer than suns like ours. But fuel is finite. Over cosmic times, the raw material for star formation runs out. New stars become rare. As star formation declines, the sky will dim. Galaxies that once blazed with newborn stars will grow quiet. The cosmic microwave background will cool more. It is already a faint whisper from an early hot time. Over unimaginable spans, it becomes colder and harder to detect. Expansion makes things lonelier. Space keeps stretching, and distant galaxies slip beyond the horizon. When that happens, their light can never return. The night for an observer inside a single galaxy will look emptier and darker. Eventually, only local stars and remnants remain visible. Long-term processes also matter. Black holes slowly leak energy and evaporate through Hawking radiation. If protons decay, then matter itself could change form over stupendously long times. Those are speculative points, but they show how the universe evolves from bright youth to a quiet, cold future. So Olber's paradox taught us more than why the sky is dark tonight. It told us that the universe had a beginning and that it changes. It also pushed us to ask about endings. If the cosmos cools into a dark sea, what happens to information, to entropy, and to everything that once burned bright? Quantum mechanics and general relativity. You stand between two pillars that both work astonishingly well. One governs the tiny, the other rules the large. But when you push them together, they fight. Quantum rules insist information is preserved and that probabilities evolve in a neat, reversible way. General relativity treats space-time as a smooth stage that curves around matter. Put a black hole on that stage, and the two descriptions clash. The conflict shows up as the black hole information paradox, and in other deep puzzles we have met. Physicists pursue several routes. String theory replaces point particles with tiny vibrating strings. In some versions, it produces fuzzball-like objects that store information without a singularity. Holography suggests our three-dimensional space could be encoded on a lower dimensional boundary. That idea led to precise tests in simplified settings called AD-SCF duality. Loop quantum gravity takes another route and builds spacetime out of discrete bits. Each approach changes the rules in its own way. There are also hybrid ideas. Soft hair, quantum memory ideas, and the no-hiding insight from quantum information offer mechanisms where information is not lost, but moved or recorded in subtle correlations. These ideas borrow tools from information science and from geometry. Experiment and observation try to guide theory. Gravitational wave detections probe black hole mergers. Searches for Hawking-like signals look for tiny emissions. Tabletop tests of quantum gravity and precision clocks push the boundary in the lab. So far, the experiments give hints, but no final answer. So, what will break first? Or will something new emerge that makes both pillars look like approximations? Will space and information turn out to be the same thing? If these pillars cannot be joined, then our textbook laws are only local patches. Physicists pursue three broad possibilities. One is that a single deeper theory will replace them. String theory and holography aim for that outcome. They suggest spacetime and particles emerge from more basic degrees of freedom. Another route is that spacetime is discrete. Loop ideas and quantum geometry change the substrate of reality. The third is that information rules. Soft hair and quantum memory ideas treat information as fundamental and show how it might be stored or released without breaking quantum rules. Recent work blends these views. The fuzzball picture from string theory gives concrete microstates that replace a black hole interior. Holography produces precise mappings, where information on a boundary encodes a bulk spacetime. Soft hair proposes that low-energy fields on an event horizon record quantum details. The no-hiding insight from quantum information points to where lost data could go. Together, these ideas sketch possible escapes from paradox. Experiment points the way, but does not yet decide. Gravitational waves let us test black hole mergers for unexpected signatures. Precision clocks probe tiny deviations in how time flows. Searches for Hawking, like radiation and tabletop probes of quantum gravity, push the frontier. Those observations may rule out some approaches and support others. Now consider the stakes. If a unifying framework wins, then physics gains a cleaner foundation, and new technologies could follow from understanding information and spacetime. If no single view works, then we may need to change logic itself, to accept limits on information conservation, or to modify causality. Either outcome would rewrite how we build technology and how we think about reality. Which future do you find more plausible? Share in comments.